Fold your paper in half. Roma, that's you. Fold your paper in half.
Oh my gosh.
No.
I would not want to eat gold plate. That's weird. That's really cool. It's edible. Yeah. Is gold edible? Well, they can make it edible.
It can be poisonous on greater amounts. It's a heavy metal.
No, but they
All
can
right,
make it
so
edible.
it'd be an expensive poison. All right, so chemical kinetics.
Like, if you're going to poison me with gold.
I'll keep that in mind.
Oh, wow.
Okay, chemical kinetics. So again, when we talk about chemical kinetics, we're talking about the speed of the reaction. How fast is the reaction happening? So chemical kinetics, it's a study of the speed or rate of a reaction. And it's under various conditions.
Study Z of Z.
Okay, so the things that you're going to have to know about this is it's going to be in molarity per second, something along those lines, some type of concentration over time, or it could be pressure, gas pressure over time. So when we look at this, typically, the most commonly we see, first of all, it's going to be a molarity per second. So it's going to be something dissolved in water, right? Your reactions are going to be double replacement reactions a lot of times, or acid-base reactions dissolved in water. Some type of concentration over time. And you can also have gases. So instead of concentration, you can also talk about pressure in that terminology. And again, if you think of pressure kind of like that increasing or decreasing concentration, you kind of think that way. But basically, it's the rate. Oh, strangely, it's the change in something over time, right? Isn't that speed, rate? Change in distance over time would be speed. So in this case, the reaction rate is the change in some type of concentration over the change in time. Whether you've taken physics or not, you've all studied that equation for speed, distance divided by time, the change in distance divided by the change in time. Okay, so what we have here is collision theory. And collision theory says that collisions between particles must occur and be effective for the reactions to happen. Okay, when I say particles, it's okay, just turn it off. When I say particles, again, when you have molecules hitting each other, again, they have to hit each other. They have to touch each other before there's going to be any type of bond breaking or bond forming, right? So you've got to break bonds and you've got to form bonds. And when they hit each other, they end up breaking the bonds that are, it's almost like they exchange bonds. They exchange bonds for those that are more potentially have less potential energy in them. And so when they hit each other, they have to hit each other, first of all, hard enough, and then they have to be in the right orientation for that to happen. So It's all about the collisions of the particles. So this collision theory is saying, hey, this is how we think reactions between different chemicals happen. They have to collide with each other. So the collision between the particles must occur. So they have to hit each other first. If they're not going to hit each other, nothing's going to happen. And be effective for reactions to happen. Now, the word effective is an important one because you'll see that on the test a lot. In your answers, when you're explaining stuff, you want to talk about not just collisions, but effective collisions. Because things can hit, but if they're not effectively colliding so that they have an effect, there's going to be something happening from this, then they're ineffective. They're ineffective collisions. So when you have your explanations, talk about effective collisions. If the temperature's too low, the particles will collide, but not with enough energy to do anything, so they're ineffective collisions. Okay, so they have to be of sufficient energy to break and make bonds, the collisions. Breaking bonds requires energy, right? Overall, that's what happens. And I'm going to put and make, but really it's all about breaking bonds, right? So they have to be of sufficient energy to break the bonds. And remember, they have to overcome the activation energy barrier. So I'm going to use some phrases that they might show you on the test here. So overcoming that activation energy barrier. So that I'm going to put that in quotation marks because when you talk about effective collisions, they have to hit hard enough to break the bonds. Okay, so when we have that, you have that in your brain. You should have that. So look right here. You should have this. Remember we talked about here's the reactants, here are the products. So this would be an exothermic reaction, right? So we have the activation energy. Here in the activation energy, part of that energy is for breaking the original bonds. If you've got two chemical compounds together, don't you have to break them apart? So that's a part of what that activation energy is there for. It's breaking those bonds that are there. So when we talk about this, they have to overcome when those molecules, this is where the energy is coming from. When we say activation energy, this is where the energy is coming from to get that whole reaction started. It's the motion of the particles. The faster the particles are, the more energy they have, the more often they're going to collide and hit. So first of all, the collisions have to be of sufficient energy. They have to be moving fast enough, right? If I have a car and I'm going to hit you with it, let's be a little violent here. Then if I'm just barely moving and I hit you with it, it's really not going to do any damage to you at all, right? You're just standing there. Like if I'm just inching along,
Yeah.
I mean, you're going to move, but it's not going to hurt you, right? If I'm going 15 miles an hour and I hit you, it's going to be doing a little bit more damage, right? If I'm going 70 miles an hour, you increase the speed, right? Without going into any equations, you increase the speed and there's more energy involved there, yes?
They'll kill us.
Yeah. So when we talk about this, sufficient energy, a lot of it has to do with temperature, right? Because if you heat them up, you speed the particles up, right?
So the hotter it gets, the more crazy.
In most cases, yeah.
Like the entropy increases. Like the chaos within the.
You can think of it like kind of like that's going to happen in many cases too. Not always, but yeah. But the key here is when you increase the temperature, you increase the kinetic energy. It's mass times velocity, right? Ke equal 1/2 mv squared. So when you increase the speed, the velocity, you increase the overall energy. And you hit something with more energy, it's going to do some more damage, right? So you have to have them going with a sufficient amount of energy here for it to work. The next thing is, it's not just a matter of hitting them. You have to hit them effectively. It has to be in the right spot. So these collisions must be effective. Here's that word effective again. And what that means is It must lead to a reaction. Specifically, it means it has to be in the correct orientation in space. If you have a double replacement reaction, and let's say you have, let's see, and I'm just going to make something up here, okay? Let's see, let's do NaOH. Okay, so let's say we have sodium hydroxide plus hydrochloric acid, right? So here's the sodium, here's the hydroxide, right? Here is the hydrogen, and here's the chlorine. Well, I know that the sodium is going to hook up with the hydrogen, so this is that the sodium is going to hook up with the chlorine, right? So here's Na, and here's the OH minus, right? If these two hit together, where this piece, the sodium hits the hydrogen and the hydroxide hits the chlorine, nothing's going to happen. It doesn't matter how hard you hit them, nothing's going to happen because the sodium is going to hook up with the chlorine, right? So in order for this to happen, then the sodium has to be down here, and the hydroxide ion has to be up here. So now when they hit each other, they're going to be in the right orientation.
Then they're going to make water and salt.
So it's not just a matter of them hitting each other. They have to hit with enough energy to break those bonds, but they also have to hit in the right orientation. The bigger the molecule is, the more difficult the orientation is to get just right. Does that make sense? Especially when you talk about catalysts, enzymes that are biological catalysts are so important because usually the molecules that are being used inside an organism are massive molecules. They're not little organic compounds like sodium hydroxide, things like that. They're much more massive, and so getting them oriented in the right space, if you didn't do that, it would take a ton more time to get the reaction to happen. So those catalysts are incredibly important in biological organisms. There's no way we could function if we didn't have the catalysts in the body at all. So these collisions have to be with sufficient energy. They have to be effective, and that means in the right orientation. And then the other thing that you need to know about this collision theory is, remember, we talked about the kinetic molecular theory. Particles are in constant motion. And remember that if we increase the temp, we increase the speed of the particles, and that increases the kinetic energy. So the way that we increase the energy of this is to increase the temperature. And the number of collisions has to increase. When you increase the speed, aren't the number of collisions that happen going to increase too? Yeah, so you have a greater chance of them being oriented correctly. There's one other video I'm going to show you. Yeah, I think I'll show it to you with this section. I'll probably show it to you now in this unit and then also in the next unit too, but it has to do with equilibrium. Many equations, many chemical reactions can go forwards and backwards, right? A lot of times in chemistry, especially in first year chemistry, we do a lot of reactions that are only one way, like setting stuff on fire. Yeah, those are the coolest reactions. And really, it's difficult to unset something, to reset so it's not on fire anymore, right? So some reactions can't be reversible, but there are a lot of them that are. And when you have those that are, once you get so many products, then when the collision's happening, when it starts they're still happening even in the products, some of them go back the opposite way. How much of them do depends on how reversible the reaction is. How much energy is required to go back the opposite direction. Do you have enough energy of these product particles colliding that they can go back and make reactants? Or do they have to heat up even more to get enough energy? How much energy is required there? Okay, so if you increase the temperature, you have more collisions. And more collisions means you have a greater chance of having effective collisions. So you increase the temperature. I need to write something else here. You have more collisions and you have greater energy. More collisions with greater energy, right? And when you have more collisions with greater energy, you have greater chances of having effective collisions. Okay, and this last little piece right there, effective effective collisions. That's the key. That's what you'll have to explain. If they're going to give you a free response question on collision theory, you can guarantee that you're probably going to have to explain this. What makes the collisions effective? If you increase the temperature in these, you increase the speed of the molecules. That increases kinetic energy. So they hit harder, and they're going to hit each other more often, and that increases the chances of having effective collisions. They're hitting more often, they're hitting harder, greater chances of having effective collisions. Okay, so on the other half of that page, let's look at the other half. Let's put some graphs over here. So I'm going to make a split down the middle of this so that I make sure I have enough room for my graphs here. Okay, so the first three that we're going to do are just really straightforward. We talk about the first two especially are just the energy of activation. We've already done these graphs before. So when we have these first two graphs, this is going to be the reaction.
Can you scoot it?
And this is the potential energy, right? We've done these graphs at least 3 different times. So here we have the reactants. They have a little bit of activation energy, and then down here we have the products, right? So let's pick a different color. So the more you label this, the better. Here we have up here the reactants up here, so we have reactants. Here we have products. Here, what is this label right here from here to here? What energy is that? The enthalpy. Here's delta H. And then this is the activation energy, the energy of activation. This is a normal exothermic reaction, right? Now, we do another graph and we set it up a similar way, same way. Okay, same way. Here, I'll let you catch up. So I still have the potential energy over here. I have the reaction. If I wanted to, I could come up with a reaction. Ooh, look, X plus Y yields XY. I could have the exact same reaction on my graph down here. X plus Y yields XY. Synthesis reaction, right? Here I have my energies here. Here's my activation energy, right? Up here I have my reactants. my products. I've got another where I've got it, it's an exothermic reaction. But now what I'm going to do is I'm going to draw a different one where it's going to go right through here. This is with a catalyst. So now I'm going to kind of shade this in right here. Right here is the energy required with a catalyst. So I've lessened my energy of activation. So this is with a catalyst. Yes, this is not new to you, correct?
Catalyst lowers.
With a catalyst, it lowers the energy of activation. There we go. Okay, I'm going to throw one more graph on here that's totally different. I'm going to get a different color pen or a marker or something. Do this graph a little bit differently. And the reason I'm putting this in here is because they had this graph on the test, on the question, and the students actually remembered it. And you're not supposed to talk to me about the test when you come back, but they were really peeved about this particular test, this particular question, and they asked me about it. So I'm going to put this one down here, and this is different. And I'm only putting this on here because of that one question. So, and I don't know if I gave this to you before. Did I show you a graph that looks like this? Yes, no. No? Does that not look weird? It is the exact same thing that we're doing here. So here we have, it's a different reaction. We've got our potential energy over here. We've got our reaction going across here. And what they did is they said, okay, fine. Where's the energy of the reaction? Where's the activation energy and all that good stuff? Here, what's delta H? It's 0. That's what they were doing here. So delta H equals 0. However much energy heat you started off with, that's how much you ended with, right? So again, here's my activation energy. Right here, it's all activation energy. Now, I think a few of them got that, but a lot of them, it just threw them totally off, and they were thinking, what is that? So the only reason I'm putting that on there is just so you can see it and not be freaked out about it if they have it on there. They'll come up with something new and totally different that we haven't gone over. So this one's just to kind of show you, hey, yeah, there's a weird one out there. But these two are our standard ones. Yeah? You should recognize these and be able to label those really easily. If you can't, there's a problem. You need to study some more. Okay. On the other half of this, what I'm going to do is I'm going to show you the hang on, I'm going to get the name wrong. Is it the Boltzmann? Was that what they called it? I thought there was another name inside there. Something / Boltzmann. What was it? Maxwell-Boltzmann. Yeah, thank you. So the Maxwell-Boltzmann things are going to look something similar to this. And let me grab a different pencil. So let's do this for something like the decomposition reaction. Say H2O2 is going to decompose to water and oxygen. I'm just giving you this just so you have an idea of, hey, this is kind of what we're talking about. It's not going to be just giving you a reaction, okay? So when you have these types for this first reaction here without a catalyst, so the first one's no catalyst, then here you're going to put number of collisions. Okay? So these are the number of collisions, and this is the energy of activation. Again, no catalyst. So I'm going to draw my graph. It's kind of like a bell curve right in here. Okay. And then right here on this end, I'm going to put a little section down here drawn in. These are the number of effective collisions. Number of effective collisions. That's without a catalyst. Let's do the same where you're looking at number of effective collisions. So these are all collisions, right? This is the activation energy, and we can talk about numbers of collisions here. So these things are colliding, right? But there are not as many effective collisions, yes? So of all these collisions, right, of all these collisions, these are the ones that are effective. These are the ones that have enough energy. Because let me word it this way then. If we're looking at this graph as on the x-axis we have enough energy, only these down here with this energy are going to have the ones that are going to be effective collisions. So you have a lot of collisions, and they're not necessarily going to do anything. Okay? With a catalyst, we're going to set it up the exact same way. So we have number of collisions, and we have energy of activation. This is with a catalyst. We have a similar looking graph here. And now, if I were doing this one, it would be about right here, right? Is that about the same?
Yeah.
Yeah. But now with a catalyst, we get more effective collisions. So they might present the material to you in this way. It's just another representation of saying, hey, without a catalyst you have this many effective collisions. With a catalyst you have this many effective collisions. Yeah? You're going to have a lot of collisions that don't do squat. Now, I want to do two more graphs of this same thing. Here, all the parameters were the same temperature, same concentrations, everything. All we did is we added a catalyst, right? Okay? So, same reaction, change the temp. So that's what's going to be below here. So same reaction now, let's change the temperature. And I'm going to have to make these a little smaller because I'm running out of space. So I'm going to go ahead and put this space here. Now let's look at it. So we have number of collisions. Let's lower the temp. Will we have as many collisions if we lower the temperature? In this case, our graph looks more like this. That's the lower temp. That's what our graph looks like. And our effective collisions are going to be down here. This is no catalyst, so I'm going to put no catalyst in there. If we lowered the temp and we added a catalyst, then our number of colored in stuff would change over here. Yes? So lower temp right here. So we don't have as many collisions. I should have made, okay, so my graph is smaller, so it should be up a little bit higher there. I'm sorry. So we're going to have less, my graph will be higher, but it'll also be more narrow too. Not as many of those collisions will have the energy either if we have a lower temperature. So we're doing two things. We don't have as many collisions in a certain time span even, but then we also have where there are not as many collisions at the right energy level. And then if we increase the temperature, we have a much, okay, I'm going to have to run out of space here. We have a much bigger, broader graph, right? So this is increased temp. No cat. No catalyst. So neither of these have a catalyst. I'm sorry, my graphs aren't as good as they should be. I ran out of space here. No catalyst. So when we compare these, these are pretty similar with the catalyst without. Here we've messed with the temperature. We made it cooler, so not as many collisions and very few effective ones. Some of them will be effective, just not very many. And then here we increase the temperature, we increase the energy, we have a lot more effective collisions on here. Now there's going to be a sweet spot in there. Sometimes you can get too high a temperature. And let me see if we have pretty pictures in the book. Do any of you guys have your 56205 with you? Let me see if there's some pictures, pretty pictures in here. No graphs. Why would they not put graphs in here?
Your blood did?
I was looking for this and it's right here. Right here.
It's like if everyone else would bother me, you. You know, it's kind of like a friend.
I need to take a picture of the other side.
Send me that golden one.
Okay.
Okay, so that's 52. We might have some good pictures.
Wait, so is that actually, like, those are actually, like, a golden retriever, regular?
Are you still talking about that dog?
Yes.
Somebody made it a golden retriever to a Dachshund. That's just wrong.
And they made it a golden Swede dog.
Yeah, I'm not seeing the graphs in here. Yeah, I see the first two graphs on page 584, but I'm not seeing the other ones on there. I put the other ones on there because they showed up on the test. So again, I don't know that the questions weren't that difficult, but when the graphs don't look like what we think of them as wanting them to look like, then it kind of throws people off. These are the two graphs that are most important. So put a circle around those, do something, but these are the two graphs that are most important here. Okay?